Are you still in California, Lucas?
No, I am now safely back in Cambridge. We've been back for about a month, and I miss California, but it's nice to have all my stuff.
I don't think you missed it today because we've had wildfires and it's not been good.
Yeah, no, that's true. I'm really glad.
Waves, wildfires, COVID, so it's not necessarily the best place on earth. It's very likely that Boston is a better place.
It seems like the fires just get worse every season, or certainly aren't getting better.
Yeah, so here the thing that worries everyone is that they start too early.
Yeah.
Usually they come later after like the long summer drought, October, maybe November, if it doesn't rain in November, but here they really start early. So it may not be the end for this year.
It's a scary prospect.
Yeah, it's not good. Yeah, I agree.
Yeah. Yeah, things are actually pretty nice in Cambridge. Places are open. People are very good at wearing masks here.
I see. So the undergrads are back?
No, they'll come back in a week, basically. So they'll
In a week, okay. And it's like only a quarter of the class, right?
Yeah, it's pretty much just freshmen. I think in principle they were going to allow up to 40% capacity if another 15% of students sort of needed to be on campus to do work, but I'm not sure they actually filled that out.
And you're going to do a class in-person teaching?
No, everything's going to be remote.
I see. So the student on campus, they're going to be on Zoom to go to classes?
That's right.
I see.
I'm not sure how it's going to work with the students who are on campus. I mean, I just don't know what they're going to do because there are very strict rules. Like it's going to be a closed campus. I think there's like no overnight guests allowed, like even between different undergraduate housing. And I'm pretty sure you're not really allowed to like go into other people's rooms. You can only like hang out in common areas, and yeah, you're not going to class. You're not going to sports or clubs or anything like that either. So
the gyms are closed and everything?
I assume so. Yeah, I haven't checked, but I'm not really allowed into the office unless I get special dispensation. So I assume the gyms are closed.
I see.
Yeah. So hopefully they find something to make it fun.
Yeah, hopefully that. Well, you can watch the convention.
Yeah, that is something they could do. The real college experience.
Yeah. And so you're doing the chair for the session, Lucas?
Yep. So I'm going to introduce you and I guess close things off. It sounds like Lihua and Yaniv are going to handle questions. I don't know if
yeah. Stephen is, I think he's hiking, so I was planning on also enlisting him, but I think he's hiking. So,
yeah.
And you're the chair tomorrow as well?
No.
Okay.
No. Yeah, I hear you're giving the same talk twice so that people can.
Yeah, one is for the Asian audience, I suppose. Yeah. And just looking at time zones, because in Europe it's very late now. It's like 2 a.m. So, and even on the East Coast it's quite late. So I don't know, like this time slot is it like for Asia or I don't know.
Tomorrow it's Peter Grunwald.
Okay.
He's the chair. Okay. And remind me, my responsibilities as a chair, aside from introducing Emmanuel and saying goodbye at the end, is there anything?
Yeah, just like the usual, like on the usual conferences, chairing essentially.
Yeah, don't spend too much time on the introduction, Lucas. Okay.
I'll try to resist listing every single accolade you've ever gotten.
No, 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 no. Yeah, like, okay, well, I know it's a joke,
I'm just
but
teasing you. Don't worry.
you know, it's better if we spend as little time on the introduction as possible.
Here, I'll send you the text I was going to use. You can tell me if it's too long.
Yeah, just be very
Right.
brief. I think it's better.
Yeah. I just sent you the text I plan to use. You can tell me if it's not good.
Is it on by email, you mean?
No, I just sent it by private chat on Zoom.
Yeah, that's perfect. Yeah. The shorter is the better. Yep.
And I imagine we're meant to start, like I am meant to start introducing at 8. Should I start at 8 sharp or let stragglers come in, or?
Yeah, I think that's fine.
Okay. Emmanuel, do you want any kind of 15-minute warning or something like that, or 5-minute warning?
Yeah. Yeah, 15 maybe.
15-minute warning, okay. And are there going to be questions at the end, or only live questions during? So is he going to the full hour, or?
Well, as you like, well, everything is possible.
What do you prefer,
We're
Emmanuel?
going to try to handle as many questions as possible with Liwa and Yaniv.
Yeah.
And I think we can, Liwa and Yaniv and I, we can take live questions in the end.
Are the questions just going to be in the chat, the like public chat?
Yeah, that's what they do. Yeah.
And I'm not sure I have an actual venue to give you a 15-minute warning, Emmanuel, aside from interrupting you, which I'd rather not do. So.
Yeah. Well, you're on the side screen, so you can just raise your hand, and at some point I'll see you.
Okay.
So, you know, like even when we're in person, like usually you wave or something.
Sure.
And,
Yeah,
you know,
if
if
you
you
can see my
wave, I'm going to get, you know, I see you right now, so I think I'll know that, you know.
Great. I'll do that then. And can anyone unmute themselves during the call? Like, am I responsible for making sure that everyone stays muted so that Emmanuel doesn't get interrupted by accident?
No, that life and I will handle, Lucas.
Okay, great.
Yeah, yeah.
All right, that's 8 o'clock. I want to make sure we have plenty of time for this amazing talk. So it is my great pleasure to introduce Emmanuel Candace as our speaker. Professor Candace is the Barnum-Simons Chair in Mathematics and Statistics, Professor of Electrical Engineering by courtesy, and co-director of the Data Science Initiative at Stanford University. If I tried to list his awards, he wouldn't have time to deliver his talk, so I'll just mention that he is a member of the National Academy of Sciences and the American Association of Arts and Sciences, and he's a MacArthur Fellow. And without further ado, please take it away, Professor Candace.
Thank you very much, Luca. Thanks for the gracious introductions, and thanks to everyone for tuning in. I wish I could see you in person, but that is not possible. And I, however, hope that we'll get through this pandemic quickly, because if one thing is for sure is I miss these scientific meetings in person, and I miss non-virtual interactions with my stats colleagues. And so I hope to see you soon. So what I've prepared today is to talk to you a little bit about a wonderful field of research known under the name of conformal prediction, and tell you how it stands today in 2020. So I'd like to thank Rina, Aditya, and Ryan for actually introducing me to this great field of research that has really changed my research agenda over the last year or two. So machine learning 15 years ago, this was a hot application, predict movie ratings. And so I think we can all agree that whether you get this right or wrong does not really matter. It's without any sort of consequences. But fast forward to today, people use machine learning. Of course, it's known also in the popular press under AI in very sensitive applications. So you're going to see snippets from publications in the United States. Here is the Washington Post. AI systems or machine learning systems are used to recognize drivers. There's a company that sells AI tools or machine learning tools to assist judges in making critical decisions. For example, whether an inmate gets paroled, whether a person gets bail. And so I cannot think of a more sensitive applications. The stakes are very high here when you employ tools like machine learning. HR departments in lots of companies worldwide use machine learning tools to recruit employees, people like yourself, people listening to this audience. The promise of AI for medicine and healthcare is great. We hope that it will improve healthcare and medicine, And so again, we're very far from the early application of machine learning, as for example, to the Netflix right now, the stakes are very high, and it's extremely important to get things right. At the same time, I'm sure everybody has heard about concerns about biases introduced by these learning algorithms. And certainly there's great awareness in trying to address these concerns. And so we'll discuss a little bit about this as well. So as we're looking at modern applications of machine learning in sensitive applications, I think it's extremely important for us, statisticians, to be able to convey uncertainty and reliable outcomes. Let me give you an example, perhaps. Let's say that we have University X, let's say that's Stanford University, that wants to partly automate its admission process. In particular, let's say that a university wants to know how students will fare if admitted. And let's say that we have a quantitative outcome that we're interested in predicting. For example, this might be the GPA after 2 years of undergraduate education at Stanford University. Now we have lots of previous students and we have a pool of new applicants, and they come with their covariates, and the covariates might be the high school they're attending, the kind of courses they've selected, their grades, obviously, their ACT scores, their social economics background, their level of physical activities, outside curricular activities, and so on. And so we have all these covariates. We can try to predict how a candidate student will do. And we're going to pass this through, let's say, a neural net predictor, and the neural net fits 3.62. And the question really is, what is an admission officer supposed to do with this? And in general, what is a policymaker supposed to do with a point prediction? Again, we're dealing with prediction that lead to actions. It's extremely important to understand the cost of the wrong actions. So we need reliable systems. And one way we should convey uncertainty and reliable outcomes, I believe, is in the form of prediction intervals. That is, we should not ask a system to just return a point prediction. Rather, we should ask the system to return a range of possible values with the confidence that 90% of this time, the true label we care about belong to this range. So this is what we're going to call a prediction interval from now on. And we're going to try to rely on trying to have these black box algorithms produce a range of predicted values for the outcome Y of interest, so that we're correct 90% of the time or 95% of the time, or whatever percentage you set. So this is the goal. And why is it that we're not seeing prediction being communicated that way? I think one of the reasons is that today's predictive algorithms are extremely complex. You can just think about gradient boosting or neural networks. These are black boxes that are, they're algorithms that are far beyond simple regression, and it's very hard to assess their uncertainty. Yet, this is nevertheless what we're going to do in this lecture, thanks to the wonderful tools underlying conformal prediction. We'll see that it is possible to use black boxes, however complicated, and still be able to return valid predictions in the sense I defined earlier. So how do we predict with confidence? Well, one naive way, and I know I'm talking to an audience of professionals, so you'll immediately see the flaw in my presentation. One naive way might be to actually fit a regression function. This is the red curve we see on the left. Look at the residuals and plot the histogram of the residuals. This is what we see on the right over here. Take the quantiles of the absolute values of the residuals and build a predictive interval, a prediction interval, to be at point X, the regression function plus or minus the quantiles of the residuals. I think everyone knows that this will never work in practice because, of course, we're overfitting. The residuals are much smaller on the training sample than they will be on future samples. The in-sample residuals are too small. This is, of course, obvious when you use neural nets, where sometimes neural nets achieve zero training error, which means that we would get confidence bands that have absolutely zero width. And so we need to do something else. So in a wonderful paper started from the late 90s, we learned that predictive inference is actually possible under no assumption whatsoever, no assumption on the distribution of X and Y. And so I show you here the early paper, and I want to kind of highlight some pioneers in this field. The field largely evolved around Vladimir Vogt. He's the person who contributed the early papers and has contributed to conformal prediction up to this day, still making great contributions as we speak. From the stats community, I want to single out Jing Lei and Larry Wasserman from CMU, who recognized the importance of these ideas and were able to port them into our field of statistics and make great contributions on their own as well. So what's the key idea underlying conformal prediction? The key idea is, of course, to look at holdout residuals. That should not come as a surprise. Instead of looking at in-sample performance, we're going to look at out-sample performance. And so instead of looking at the quantiles, which we see on the left of the residuals on the training set, we're going to look at the quantiles of the residual on the test set. We're going to look at the quantiles, and we're going to adjust the prediction bound to be the regression function plus or minus the quantiles of the out-of-sample residuals. The rationale is, of course, very clear that 90% of future test points will fall within this band, sort of by definition. So this can be articulated in a very rigorous statement, which is this, that if I look at, let's say, the 90th percentile of the absolute values of the residual on the holdout set, what we're going to call the calibration set, which has not been used for model fitting, and I construct a prediction interval in exactly the way you would expect, it's the regression function plus or minus Q, then the theorem is that this achieves the coverage you like. All right, so this is a kind of a nice result that may not be very surprising to you, but it's still there. And we focused on residuals, but what the field has developed is you can think of any statistic you like, we're going to call them conformity scores. I've shown you conformity scores, which is essentially the distance between a true label and the prediction. But why stop here? You can choose any score you like, and you can construct predictive set by exactly the same rule. You're going to include Y in your predictive set if its conformity scores is below threshold. I almost want to call this conformity scores Z-scores. So you include Y if its Z-score is below threshold. And of course, you see the connection with hypothesis testing we're all familiar with. So now with threshold, well, the threshold would be just the quantiles of the conformity scores calculated on the calibration set, the holdout set. And so the general result underlying conformal prediction is that if I take the quantile of the scores, the holdout scores, then and I build a predictive set that way, then no matter the distribution of X and Y, the Y belongs to the confidence, the prediction set 1 minus alpha of the time at least. So this is all great, and the proof is actually very simple, and I'm sure that it will remind people working in non-parametric statistics of what they do when they use rank tests. So let's say you give me data, xi, yi's, which are IID or more generally exchangeable. Then the immediate implication of this is that the scores are themselves exchangeable. And therefore, when I look at the score of the test set on the test point, it is the rank of this score is equally likely to be any of the ranks. So this is why I indicated before. Below, the rank of your test score is a discrete uniform random variable. And because you just take the quantiles, the right quantiles, then you can say very quickly that the point S of xn plus 1, yn plus 1 will be to the left of Q by definition, 1 minus alpha fraction of the time, and therefore you achieve coverage. So it's just using exchangeability of the data that you have. Okay, so that's all great. And so now what we want to think about is, well, we have a general methodology. We can use any scores you like, but really, which score should we use? So the first part of the talk has to do with, let's think a little bit about what we should score and how we should score. So I want to go back to the problem at hand. That is, we have a y, we have an x, and the goal is to predict, to give a range for y at any given value of x. Of course, if I knew the conditional distribution of y given x, which is indicated by these red curves, I could calculate the high quantile, I could calculate the low quantiles at each point x, and I could connect them, and I would give you what you want, which is really the prediction interval that are what are in a sense perfect. Now observe from this picture that the lengths of these intervals can vary greatly depending on where you are in covariate space. So again, the blue curves are the true low and high quantiles of the conditional distribution. The red-pink region is a region that this method I described returns. And so you see that you have a conditional mean, and you see that you have an interval of fixed width around the conditional mean. So you adjust the conditional mean by the quantiles of the residuals. And so what we can see that there's a problem with this, which is that the width of the true intervals vary greatly with x, but here the width of the interval that conformal inference, at least in this form, produces is constant. You're not adaptive. You cover, but you're not adaptive. So, of course, nobody knows the distribution of y given x. If we knew it, then there would be absolutely no job to do. And so what we can do is we can try to kind of bring in quantile regression. So one thing that puzzled us when we looked at the literature on conformal prediction is that we're fundamentally trying to estimate the quantiles of a distribution function. And if that's the case, why do you start by estimating the mean? Why don't you just go and estimate the quantiles directly? And this can be done, of course, thanks to this wonderful idea of regression quantiles from Kunker and Bassett from a few decades ago. And I'll just remind you of how this works. What I'm going to do is, let's say I'm feeding random forest or neural nets. Instead of feeding the conditional mean, I'm going to feed the quantiles of the conditional distribution of y given x. And the way it's done is by actually changing the loss from the squared loss to, I like the name pinball loss, sort of an absolute value function with slope that may not be the same. And if alpha is 0.1 here, and I minimize this, and basically I'm trying to find the empirical 10th percentile of the distribution of y given x. And so instead of estimating the mean, we can estimate these quantiles. And so on the training set you gave me, I would get the two quantiles below, and we see that, of course, the widths depend on where you are in space. Now, would this work? No, it doesn't. I might be overly optimistic. I have no guarantee that on future samples this would work. And so just on this example, we can see that if we have a target coverage level, which is 90%, the realized coverage is much below. Here, I want to open a parenthesis that imagine that you're training a neural net, then, because you're overfitting, the coverage might be disastrous. So we're going to need to adjust these quantiles, and that's where ideas from conformal regression prediction come in. So we're going to adjust these quantiles, and so what we're going to do is we hold out a calibration set, and we're going to score points in the calibration set, in this independent data set. Now let me show you how we're going to score points and what are we going to do with these scores. So the methodology is actually quite simple. I'm fitting the quantile on the proper training set, and on the calibration set, I'm just going to, for each point in the calibration set, I'm going to measure its distance to the nearest boundary. And I'm going to sign this distance with a plus or minus depending on whether the point is outside of the predicted range or within the predicted range. Right? So each point gets a score, which is positive if you're outside of the predicted range and negative if you're inside the predicted range. And so let's say I have 500 test points and I'm interested in building a 90th percentile confidence band. Then I'm going to look at the 90th percentile of these scores. That is the 450th largest values of this score. This we're going to call Q, just like before. And now the definition of the predicted interval is very simple. It's whatever I fitted by quantal regression, but then it's been adjusted by this value Q. Okay, so I'm going to enlarge or actually shrink, depending on the sign of Q, the naive prediction interval. And what we can see here is that, for example, suppose that I'm overfitting, I'm too optimistic about my coverage, then it means that more points will lie outside, so the Q will be positive. And what this will do, it will have the effect of enlarging the confidence band a little bit. On the other hand, if I started to be too conservative, then Q will be negative and it will shrink it. Of course, if I start with very good quantiles, then Q will be roughly 0 and this would barely touch it. So we can construct a prediction band like this by using ideas from conformal, from quantile regression. And when we test it on future test points, the coverage is just too good to be true, is 90%. But this is not a surprise because we're setting conformal prediction in action. And it is a theorem, as you'll see later, that the coverage has to be pretty much exactly 90%. So we have two proposals to actually construct confidence bands. The one on the left is the one that I showed you before, where you basically have a band of fixed widths around the regression function. This one is quite different, where you actually fit the quantiles and then you adjust them slightly. What we can see is that the widths of these intervals is highly adaptive. It depends on where you are in X space. The other thing we see is that the length is much smaller than what it is on the left. So you're, in a sense, more efficient. We can look at these plots with a different light. So if I look at the right plot here, you have the length of the CQR interval as a function of X. And we can see that it varies greatly depending on where you are in space, whereas the length of this method based on the residual quantile is fixed. And this plot, which we're going to discuss a lot in the future, in the next 30 minutes, is a conditional coverage. So here we're measuring coverage as a function of X, of where you are in X space. And we see that the blue curve is pretty trailing the 90% target, whereas these other methods tend to widely undershoot, then overshoot, then undershoot, depending on where you are. So think about, you have a measure volatility of a stock. You want to essentially predict future returns. Then what the orange method would do is would tend to fail to cover when the volatility is high and overcover when the volatility is low. And that's a phenomenon you see on the left. So we can also apply this to real data, obviously, and this is an interesting data set. It's called the Medical Expenditure Panel Survey, where the goal is to predict healthcare system utilization as measured by the number of visits to a doctor's office or to a hospital based on covariates such as your age, your marital status, and lots of variables I can measure about you. And so when we apply these conformal prediction algorithms to this example, both methods, and you'll see that it's a theorem that they both achieve marginal coverage at exactly where you want. But in terms of length, this is what we've seen before, but now it's real data. The method, because it's more adaptive, produces shorter intervals and also achieves better conditional coverage. So we have a way to construct prediction bands that provide better conditional coverage and shorter intervals, at least on this data set. But it's just not only this data set. We actually try to be good citizens with Yaniv and Evan, and we actually took a lot of data sets from lots of different fields. And these observations I convey to you, repeat over and over, which is that this method tends to be better at producing prediction intervals than the original method. So this shows you the importance of choosing the conformity scores in the right way. You can go one step further, and so you can do more. And so you can try to leverage quantile regression a bit more. So you see, the method we've seen so far is fitting essentially quantiles, because it's trying to learn the conditional distribution of y at location x. And then it says, but you know what, these quantiles are not capturing enough of the data on a holdout set. And so you're going to enlarge these quantiles in a uniform way. But you can do this in a much better way. So for example, what you could imagine doing is you could imagine fitting many quantiles, right? So you fit quantiles for every value of percentiles, for example, so that at any given point x, you have an estimate of the conditional distribution of y given x. You can do this by quantile regression. You can do this by the contrast trees of my colleague Jerry Friedman. You can do this in many different ways. But once you have an estimate of the conditional distribution of y given x, then naively, you would just take the quantiles of your conditional distribution estimates and say, that's my proposed confidence interval. All right, and so would this work? Well, no, it would not, because your conditional distribution has not been calibrated. And so what now you'd say, well, but I can do this for different values of the parameter tau. And so what you can do now on a holdout data set, you can say, well, on the x-axis, you see the real values of tau. On the y-axis, you see the real coverage. And of course, this is not a straight line because you're not doing a perfect job. But what you can do is you can find the value of tau over here such that on the holdout set, you achieve the target you want of 90%. So you find this value tau hat that achieves 90% calibration coverage, and you can say, and you know what? Now I'm going to use my prediction set not at the nominal value of tau, but at the value tau hat that achieves 90% coverage on a holdout set. And this would just work as well. Now, what's good about this is you can extend this to all kinds of settings. For example, you can extend this to a discrete setting, where now you think again, like we are modern, we're going to use neural nets. And as probably you know, that the layer to last layer of a neural net is a softmax layer, which estimates conditional probabilities. Now we're trying to predict a discrete label y. And so I have my sorted class probabilities over here, my class labels. And if I wanted to give you, if I were to trust this, I would say, well, you want a 90% prediction set. I will actually go down from the largest class probability to the smallest one until I reach 90% mass. And in this case, it means that I would return ABC. All right, well, what you can do is you can apply the method we've just seen exactly as they are. What you do is you say, well, I'm going to estimate class probabilities, but then I'm going to apply these naive methods, but then I'm going to calibrate it on a holdout set by checking, again, the actual coverage versus the nominal level. And so I'm going to realize that to achieve 90%, I need really to use 95% prediction intervals. And so what that means in practice is when you see an example like this, you'd say, well, I need to use 95%, so I need to include D as well. And so your prediction interval will be exactly the same as before. You will use, you will calibrate the level at which you make prediction. And you see that it does more than a method where you just shift the quantiles up and down. You're really using a lot of information about the conditional distribution to do the right calibration. So all the methods I'm describing, people might be a bit confused about what does this have to do with conformal prediction? Where is the conformity score? You know, there are conformity scores lurking in the background. And as a result, we have this result, which is not original, which is that all the methods I presented obey precise coverage. Like the coverage is essentially practically equal to 1 minus alpha. And that's what you see in experiments again and again. So for classification, again, Ley, Robbins, Wasserman, Vogt, and his collaborators had an earlier idea to actually get a prediction set for discrete labels. And the idea was quite simple. You use your probability estimates, your conditional estimate pi hat of y given x, and you select y when this conditional probability estimate is large enough. And how large does it need to be? Well, it needs to be as high, at least equal to the quantiles of the probability scores that you've seen on a holdout set. So if you conform, if you look like what you've seen before, you include, and if not, you do not. And what you're just doing here is you're thresholding, in some sense, the distribution, the conditional distribution function. Now, this can lead to unsatisfactory answer. Again, you seem to lose adaptivity. And so let's say that it's a setting where we have perfect knowledge. We know the true conditional probabilities. It could be that you conform, the threshold Q, the quantile is over here. And so in this example, which is a class label, which is easy to predict, then the thing will do the right thing. It will say, you know, I'm returning A, and the ideal set is indeed A. Here we see something a bit different. We see we're not quite sure about what the label is. It's a hard to predict case. The trouble is that the method I'm describing above returns the empty set, right? Nobody rises above this quantile, and I prefer to say, I don't know. And so what we're saying is that the threshold Q is not adaptive to X. And it's very different from the method I presented before, which really adapts to X. And so you can see this in simulations. If you use the early method, I'm calling this year 2013, you see that in terms of marginal coverage, it's going to do the right thing, obviously, this theorem again. But in terms of conditional coverage, it suffers a bit. It does not adapt to where you are, whether the method that we're advocating here adapt to where you are. So we have, for large, you know, no matter where you are in X space, we seem to achieve conditional coverage while these methods do not. And this is not something we see only on simulation data sets. We see this on real data set. This is a famous NIST data set where we're trying to predict handwritten digits via neural nets. And we can see again here that the conditional coverage for these new methods is higher than these original proposals. Okay, so in this talk, I'll present a few vignettes of conformal prediction. So one is about better conformity scores. And now I want to move a little bit towards this kind of equitable treatment and fairness ideas that we've been discussing in the introduction. So this is again my reminder that when we apply machine learning algorithm to predict sensitive outcomes, we need to make sure that we know what we're doing and that we treat people equitably. And so, of course, the call is great on statisticians and computer scientists and everybody involved to not introduce bias and not to reify the status quo. So we want to use machine learning algorithm to support important decisions. I think I've made the case that when we communicate to decision makers, it's extremely important to communicate uncertainty, and we can certainly do this through these prediction intervals that will allow us not to overstate what can be learned from these fancy algorithms. But of course, the thing we need to pay attention to is to make sure that we treat everyone equitably. That would be, of course, completely unacceptable to get decent coverage for, let's say, white people and horrible coverage for non-white people. This would lead to unfair treatment, discrimination, and so on and so forth. So what we'll see in the next few minutes is that ideas from conformal prediction can address this issue. And I'm going to go brief because I only have like 50 minutes. It's not a talk about fairness in general, but I think I want to kind of mark points of departures with the traditional literature on algorithmic fairness. This is something that people work hard on, and I see lots of good ideas. I think here you'll hear something a bit different, where we're not trying to conflate the prediction problem with the policy problem. That is, we're not trying to design an algorithm that will achieve a certain goal that either the computer scientist or the statistician has set for him or herself. Instead, we're going to decouple the prediction problem from the policy problem. And this comes from the fact that I can correctly predict that, let's say, a certain inmate has a 20% chance of committing another crime if released from jail. But this fact alone does not determine a course of action in and on itself. So we're going to try to decouple the policy problem from the prediction problem. And it's quite against the current thinking in algorithmic fairness in machine learning, where the two tend to be quite coupled. So let's go back to our example of services. Among the variables that I have to predict utilization of healthcare services, I have a covariate race. And so if I look at, and it's just observations, if I look at my neural nets to estimate future utilization, I can observe empirically that the neural nets will tend to overestimate the response for the non-white group, and conversely, it will tend to underestimate the response of the white group. What that means is if I build prediction intervals, and I know that marginally they're correct, but when I look at the prediction intervals per group, then I'm starting to see some deviation. So here, they're not big, the deviations. I tend to overcover for non-white and undercover for white. But you can imagine that there are examples where the deviations might be much larger. And so one thing you can do with conformal prediction is you can say that you want unbiased prediction. So what we're going to make is we're going to make something which is prescriptive, which is that going back to my example of college applications, I want that my range be not only correct on average, but that they be correct no matter what group you belong to. And so saying that we have two groups, male and female, the goal might be to actually construct perfectly calibrated intervals across all groups. This is what we're going to require is prescriptive. So that no matter what group you belong to, the range I'm giving you is honest. And so if we do things this way, then I think it's a nice way of communicating with the policymakers what we've learned from data about future performance. And so I think to communicate results in the form of prediction intervals that hold conditionally true on something you care about, let's say a sensitive attribute, is a good way of communicating the results of data analysis because one, it rigorously quantifies uncertainty. Two, it says, well, if your interval is long, I'm sorry, but machine learning and past experience has little to say about future performance. And three, because you're unbiased across groups, you treat individuals equitably. So now how would you achieve this? Well, let's say we have a minority and a majority group. Then they're pictured in orange and blue on my slides. And a very naive way, which would be just treat them as separate and run conformal prediction on each group separately. You might think that by doing so, you lose a lot of power, and that's probably true. That's what we observed in practice. So what you can do is when you're learning your model, you're feeding your quantiles, or you're estimating your conditional distribution, you can actually merge these two groups because you want to borrow from the experience of everyone when you actually make up your model, but then you calibrate separately. And so if you do if you do things like this, where the calibration is conditioned on the group you belong to, but perhaps the model is learned on the combination of the two groups, then you will achieve this, which is, I think, a good way of communicating what you know to decision makers. So this is, I'm quite passionate about this. So we've actually run this on the MEPS data I presented before, and we observed that if we're not doing this, we might get different coverages depending on the group you belong to. But if we use the method, and perhaps I'll ask you to focus only on the last row, if we use this method with the CQR method I presented earlier, which has been calibrated separately on the non-white and white group, but trained on both groups at the same time, then you'll see that condition on group membership, you achieve exact coverage, and these are the lengths of the intervals you get. So again, we see that when we do this, of course, we can use this with any conformity scores we like. Two things pop out, at least in our experiments. When we use CQR, we tend to get shorter intervals, and joint training is usually more powerful, at least in the examples we've tried. So as I mentioned, I'm quite passionate about this. I like the fact that we're not trying to bake in ideology about what it means to be fair. To me, even the definition of fairness is problematic to me. What we're trying to do here is to try to present the fact to policymakers in the most unbiased, informative way that we can, so that this does not lead to unfair practice or discriminatory practice. Because we're not trying to bake our own definition of fairness, I think that what we're doing, we're not conflating data analysis with the decision world, we're just informing decision makers. I think we empower the users, the policymakers, instead of what I'm going to roughly say, instead of playing gods. And so I think this method, by treating everyone equitably, by being prescriptive about the kind of guarantees you have for each group, means that hopefully will not do harm. Okay. All right, so I'm going to move on and show you another vignette, another application of conformal prediction that I like a lot. And this has to do with counterfactual inference. And this is joint work with Liouville, who happens to be on the line with us tonight. So I guess most statisticians are familiar with the counterfactual inference problem. For those of you who are not, this might be a bit fast, but let's try to kind of bring you into counterfactual inference if we can. I have individuals, and they have their covariates X. And based on their covariates, I might assign them to a treatment group, or I might assign them to a control group. So let's say I'm going to randomize an experiment where an individual comes, I see the covariate X, and I flip a coin with probability EX, which is called the propensity score in causal inference. And if the coin is heads, you become a treated unit. If it's blue, if it's tail, you become a blue unit. So blue people are people who receive the placebo. Red people are people who receive the treatment. And so going back to, of course, the work of Neyman and Rubin, we are in the setting where we have potential outcomes, right? So Rubin says that we have the science table, and the science table in my example has two rows, is that it has the thing I can actually observe, and these are the response of these treated individuals and the response of these control individuals. There's also this counterfactual world that I do not get to see, which is what would be the response of this individual, which is paired with this one, if I had treated this individual. And likewise, I treated this person, I might be interested in asking the counterfactual question, what would be his response if I had not treated these individuals? And so this is really the core of a lot of causal inference, to actually predict the counterfactual. We only see one of the two, we'd like to know about the other one. So in picture, this is a situation we have over here. We have an individual, let's say it's a controlled individual, a person assigned to the treatment group, the control group, sorry. Therefore, I see his Y0, but I would like to ask about his Y1. What would be the response of this individual had this individual been treated? And so we can see, without burdening you with too much notation, we can see that we have a setting that looks like this, where the dark colors are people responses actually observed. So let's look at this one. This is a distribution of individuals whose X and Y are sampled from X, given that this individual has been treated, times the response given X. People here have a different covariate distribution because they've not been treated. Let's look at people over here. These people are the same as these people above, but I'm not asking about Y0, I'm asking about Y1. And so what I want to do is I want to infer about, let's look at this shaded red people. I want to infer the counterfactual, what would happen to a person that was in the control group and if that person had been treated. And so what we can see is we have a covariate shift, right? We have examples of Y1 over here, but these examples do not have the same X distribution that the target over here. So we have what we're going to call a covariate shift. There's a distribution mismatch. We are not in the setting of conformal prediction, right? So I'm going to try to make future prediction on a distribution of X and Y, which is not the same as the distribution about which I have data. And so we're going to have to deal with this problem. So just to make things clear, this is the real world on the left. These are the world of the treated units. And you can see that if your X score is low, then you have a higher chance of being traded. When your X score is high, you're over here, so you have a larger chance of being in the control unit. And then we have the values of Y1, and we can see that we cannot really use this to actually do this because of this covariate shift. Okay, so we're outside of conformal prediction. We need to adapt to this covariate shift. So how are we going to do this? So if I try to set up the problem a bit abstractly, I would say this. I would say that nature has given us IID samples from a distribution P of X times Py given X. But my goal is actually construct a prediction interval at X for new data coming from a different distribution. And the new data has distribution Q for the covariates and the same likelihood of Y given X. In particular, these two distributions, the target distribution and the training distribution, differ, and they differ in the covariate distribution, and the ratio between the covariate distribution is what we call WX, the ratio between Q and P. In our counterfactual inference problem, this is, of course, ratio of propensity scores. Okay. So I think I spent enough time on conformal prediction to explain to you how it works. You get a holdout set, and on your holdout set, you get conformity scores. You look at the quantiles of your conformity scores, and you include it if on a new test point, your score is below that quantile. But that is not going to work for us, because what we're going to experience is we're going to experience a covariate shift. And so in joint work with Ryan Tibshirani, Rina and Barber, and Aditya Ramdas, whom I mentioned earlier, we showed how we can adopt conformal inference to actually deal precisely with this kind of covariate shifts. And the answer is not very complicated, actually. What you do is you compute exactly the same conformity scores, but you reweight them when you make your histogram, when you compute your empirical distribution of non-conformity scores, you reweight them by the ratio of the two covariate distribution. And what you do now is you just take in as your threshold the quantile of this reweighted histogram. That would lead to valid prediction. And when you move back to the world of counterfactual inference, that says that, if I know the propensity score, for example, and I apply all of these methods by adapting to the change of distribution in exactly the way you've seen, then I can make a prediction for a control unit about his response to treatment. And that prediction, this prediction interval that I'm constructing, has exactly the same coverage as what you've seen before. It's practically equal to 90%. Now, you might ask, well, in practice, I may not exactly know the propensity score. And what I want to see is that in work with Liouville, we've shown that, a bit what you see in the literature on causal inference, that we have a form of double robustness. That is, if you can estimate either the propensity scores or the quantiles of the distribution sufficiently well, then this will hold approximately. And I will not have time to discuss this, but simply refer you to the paper for further details. Okay, so when we actually apply this to data, we see that, again, by applying this idea of conformal prediction, we can make valid prediction for counterfactual responses. And so the top 3 rows are, various conformal methods wrapped around BART, wrapped around boosting, wrapped around random forest. It does not matter what you use, you will always get right coverage. At the bottom, you see methods that are frequently discussed in the literature, and this dramatically undercovered. If we were to look at length, the left plot is the same as before. If you look at length, we can see that these methods, of course, depending on the method you use, you get shorter or wider interval. The blue line is an interval that you would get if you knew actually the counterfactual distribution. And so you can see that you're a little bit wider, but it's not crazy. You're wider by, at least in this example, by a factor which is less than 40%. And so, of course, depending on the conformity scores you use, the method you use, you're going to get more or less efficient. But what this shows is that you can get to accurate conformal prediction. Again, if we look at now conditional coverage as a function of x, this is the grail. Of course, nobody can actually guarantee that you get conditional coverage, but what we see for the conformalized method at the bottom using these fancy scores, we can see that over a wide range of x, which seem to achieve a conditional coverage. All right, we've been able to extend this to a setting where we try to do something more ambitious, where again, we have our control units, we have our treated units, and now we have people who have never seen before come from a new population. And so the question we ask an individual we have never seen is, can you actually predict the individual treatment effect? That is a difference between treated and not treated for that individual, of an unseen individual. And perhaps now it comes as no surprise that we can also deal with situations like this, that we can set conformal prediction in motion to actually get valid intervals for individual treatment effect for individuals for whom we miss both outcomes. And I'll refer you to the paper for this. So I wanted to tell you a little bit about other topics, but I can see that my time is up. And so I want to leave time for question. One thing we have not talked about is about data reuse. So right now, we've used what people call split conformal, which is that, we train, we learn a model, and then we use a holdout set to calibrate everything. There's a standard approach in conformal prediction, which is full conformal, which bypasses this split, but it's computationally prohibitive. So that's why I've not discussed it. With Rina, Aditya, and Ryan, I want you to know that we derived a modification of the jackknife method or cross-validation method that can guarantee coverage. So I'll just say this, and then I'll wrap up. I'll say that the jackknife predictive interval that everybody knows about, which are basically constructed on holdout residuals or even cross-validated residuals, can fail. In fact, you can show that it can have coverage equal to 0. And what we were able to do with Rina, Aditya, and Ryan was to actually modify the jackknife and cross-validation to guarantee coverage. Now, this has connections with the cross-conformal prediction, which Vladimir Volk introduced in 2015, but it's different. And this gives you the guarantees. And this can be adapted to any conformity score you like, continuous, discrete labels. It's extremely general, just like the jackknife is very general. So I'll skip this part because my time is up. I had some slides about explaining the jackknife plus or CV plus, but I gave you the gist. Like the jackknife does not have coverage guarantee, but you can modify it, or you can modify cross-validation to achieve guaranteed coverage. And this applies to any conformity scores you like. Okay, so my time is up. So I'm going to skip to the end. In the spirit of reproducible research, we've made all our work, made it available online, codes, softwares, figures, and so on. And so here you see a bunch of URLs where you can download and read about all of this if you were interested. And to summarize, I realized that I give you a very personal tour of conformal prediction. I think it's a fantastic field of research. It's at the heart of what we need to do, which is to use these sort of very fancy methods that we can't really understand, but we can wrap around these fancy methods to quantify uncertainty. And what I really like about conformal prediction, the work of Vladimir, the work of Larry, the work of Jing, is that their ideas can be applicable to meet the highest professional standards. That is, when we need to communicate the results of data analysis to decision makers, policy makers, we can really use these tools to enforce the highest professional standards. And with this, I would like to thank you for your attention.
Great. Thanks so much, Emmanuel, for an amazing talk. And I'm sure we're all clapping quietly in our muted screens. So yeah, now we have about 6 minutes for questions. So if anyone has a question, they should go ahead and raise their hand in the Zoom screen, and I'll call on you. Yes, Yaniv and Lihua did a good job of answering questions during the talk.
Well, I don't need to keep you for too long. You know, I know it's late for some of you, so.
Here we have a question on the chat from Siva. Are there examples when intervals are very large in size?
Yeah, of course. Like when it's very hard to learn from data because there's tremendous variability in Y, it's very difficult to predict what people will do 1, 2, 3 years from now. So yes, so in many cases, but I think that's what's good is like at least when you report prediction interval, you're honest about what you've been able to learn about your problem. And by reporting wide intervals, you tell clearly to the decision maker that it's not really possible to learn from data in this instance. One application where it's interesting is going back to this fairness issue. It could be the case that for different groups, I have widely different intervals. And this might be due to different things. It might be that a group is harder to predict than another. It might also be the case that for a given group, I have less data and therefore I have more uncertainty. And I think it's also extremely interesting to actually report intervals for different groups of widely different lengths. We're prescriptive that the coverage need to be the same. We don't want the lengths to be the same. But if the intervals have widely different lengths, then this might suggest to people to actually collect more data about the minority population. So for example, it's been the case, my understanding, and we've seen a lot of papers in high-profile journals such as Nature, that for a long time in the medical sciences, we're not really collecting data about women. And as a result, we know less about women than we know about white males like me. And so in these cases, you'll see that the confidence interval you tend to get for the minority group, women in this case, will tend to be larger. But what that suggests is that just about time that we collect more data about this group.
Another question in the chat from Ishmael. In many real settings, the task is binary. For instance, approval/denial of a loan, disease or no disease. I wonder whether it still practically makes sense to output confidence intervals in this case.
Well, so there are cases where you'll be very sure that of Y, and you'll, in that case, you'll be able to say 0 or 1, but you have to be honest about what you know and what you don't know. And so if I'm asking you to, let's say, I'm asking you to predict whether an inmate will commit another crime, you know, I prefer that you be honest and say, I don't know, in the form of return 0 and 1, rather than make up something and tell me Y hat equals 1. So I think what we'll see, and again, it's always the same thing. It's like, you're welcome to use the most powerful learning algorithm you want. This will just wrap around whatever you use and will communicate the results of your analysis in a way that is reliable and equitable. And if you're not able to learn precisely enough, then this will be reflected in your confidence intervals. But I prefer to say, I don't know, rather than pretend that I do know.
Great. So I think we're just about out of time now. If we can give Emmanuel our thanks again, people can unmute themselves to clap, and we'll do the same.
All right. Thank you very much. Thanks for your time and for staying up.
Thank you so much, Emmanuel. Good night or morning or goodbye, everyone.
Yeah, good evening. All right.
Thank you. Soon, just wait a minute. Zhengu will share a slide before you can start your talk.
Okay, thank you.
Thanks, Lucas. Bye-bye. Can you share your slide? Is it possible? Thank you. Bye-bye. You can start now.
Do you see the beautiful photo? Yeah. Okay.
Thank you.
If we want to keep the time, I think we start now.
Yeah.
How do you think, Siva?
Yeah, please start. Yeah.
Okay. Good day, everybody. It's a great pleasure to introduce the speaker this morning in Beijing at different times. Our speaker is Xin Sun. Xin earned his bachelor's degree from Peking University and his PhD from MIT under the supervision of Professor Scott Sheffield. He's currently a junior fellow at the Simon Society of Fellows, having worked in the Department of Mathematics at Columbia. He has just joined the Faculty of Mathematics Department at the University of Pennsylvania. Have you moved to Pennsylvania, Xin?
Yeah, I have just moved for a couple of months.
Oh, okay, I'm right.
Yeah.
And Xin is among the 3 awardees of the Bernoulli Society New Researcher Award of this year edition. Congratulations. His work, he has worked on topics like Liouville quantum gravity surface, Gaussian free field, fractional Gaussian field, uniform spanning tree, random matrix, and so on. Today, he's going to talk on quantum Liouville theory on the torus. I think I stopped my sharing of the screen. Could you share your screen?
Yeah, sure. Can you see it?
Yes.
Okay.
No, you may start. Thank you.
Okay. Thank you for the introduction, and thank you for coming to my talk. So today I will talk about quantum Liouville theory on the torus. Let me start by recall some basic facts from two-dimensional differential geometry. First of all, so we have the classification of closed topological surfaces according to the number of holes, which is called genus. For example, we have sphere, torus, genus C surfaces, and so on. Today, I will mainly focus on sphere and torus, but there are some similar stories for higher genus surfaces and surfaces with boundaries. So, and given a topological surface S, with a, we can consider Riemannian metric on S. And once we have a smooth metric, this metric will induce notions of distance, area, curvatures, and other geometric concepts. So one thing which is very important to us is the concept of conformal equivalence. So two metric G1 and G2 on a surface S are called conformally equivalent if they differ by a local scaling. Namely, they only differ by some scalar function. And my topic today, the quantum Liouville theory, it is a one-parameter family of quantum field theory. And given a parameter gamma, the quantum Liouville field with parameter gamma is a way of assigning some measure on the space of functions on each Riemannian manifold. Importantly, it satisfies the following transformation rules. The first one is very simple. It just says that if we have two Riemannian manifolds which are isometric, then the measure just relate naturally. And the second one is more important to us. It says that if we have two metric which are conformally equivalent, then these two measure on random functions, they only differ by a multiplicative constant. And in the Liouville theory, actually, this constant is have the following form. So here, this delta G is the so-called Laplacian Bartrami operator on the Riemann metric, and this is the so-called determinant of Laplacian. So I will not give the precise definition of determinant Laplacian in our talk, but we just need to know that this is a number which is associated with every Riemannian manifold. And here, this power C is having this relation with gamma, and C is called central charge. So the first transformation rule, this holds for every quantum field theory. And the second one holds for every quantum field theory with a conformal symmetry. And they are called conformal field theories. And this constant C here is called the central charge of the conformal field theory. So we can say that the quantum Liouville theory with parameter gamma, it has central charge given by this. Okay, so before I go to the mathematics of the quantum Liouville theory, let me first give some history. The quantum Liouville theory is motivated by something called 2D quantum gravity. So here, so 2D quantum gravity on a topological surface, it just means random geometry on the surface. And this is a dictionary between physics notions and mathematical terms. And the most simple quantum gravity is called pure quantum gravity. And this is simply the uniform measure on all possible random geometries. And in physics, it means the so-called gravitational background without any matters. And in physics, it's also relevant to consider the so-called quantum gravity coupled with conformal matter field. And this is a natural way of introducing a one-parameter family of random geometries, which I will talk about later. And given a random geometry on a surface S coming from quantum gravity, conditioned on it being conformally equivalent to a given Riemann manifold, then this random geometry, it can be represented as follows, just by the definition of conformal equivalence. So there will be some random function, and this random metric will be given by this form. So in a groundbreaking paper by Polyakov, he did the following things. First of all, he introduced the quantum Liouville theory, and he showed that the quantum Liouville theory is a conformal field theory. And then he conjectured that the random function coming from the quantum gravity, it is actually following the distribution given by the quantum Liouville theory. And suppose the conformal matter field has the central charge Cm, then the central charge of the conformal matter field is related by the central charge of the quantum Liouville field by this remarkable formula. And this number 26, it turns out to be the critical dimension of bosonic string theory. So I want to mention that this conjecture relation between 2D quantum gravity and the quantum Liouville theory, it's even a conjecture at the physics level. So after the introduction of quantum Liouville theory, there are mainly two research directions in theoretical physics about the theory. One is geometrical and the other is algebraic. So in the geometrical direction, so it's basically the relation between quantum Liouville theory and the 2D quantum gravity. So the random geometry induced by quantum Liouville theory is something called Liouville quantum gravity. And the random parameter maps is the discrete version of a natural discrete version of 2D quantum gravity. And based on Polyakov's work, there is a vague conjecture that Liouville quantum gravity should be the scaling limit of random parameter maps, because tautologically, since the random parameter map is a discrete 2D quantum gravity, the scaling limit of random parameter maps should be the real continuum quantum gravity, and that should be related to this Liouville quantum gravity. But this was remained a vague conjecture because the random geometry induced by the quantum Liouville theory, it didn't really well define back to then. But there are some very strong supporting evidence around 1990s supporting this conjecture. This is the agreement in certain scaling exponents in these two approaches. In the Liouville quantum gravity, there are something called Kishnik-Polyakov homological relation, which allows to compute some scaling exponent. And on the random parameter map side, there are some techniques coming from random matrix, which can also derive some scaling exponent. And in all cases where both approaches can give you a number, they will match. And this gives supporting evidence for this conjecture. And in the algebraic aspect of quantum Liouville theory, so basically, in order to solve the so-called correlation function of quantum Liouville theory, Liouville, Polyakov, and Zamolodchikov, they realized that the 2D conformal symmetry, it actually gave very deep algebraic structure to general 2D CFTs. And quantum Liouville theory turns out to be a very primary example of 2D CFT in this aspect. So although both of these two approaches remain vague mathematically, they does inspired very important progress in probability around 2000. First, in the geometric direction, the Liouville quantum gravity and KPZ relation, they gave very deep predictions about the dimension of certain random parameter fractals. One of the notable example is Duplantier's derivation of the Brownian non-intersecting exponent, which is later proved by Lauder, Schramm, Werner using SLE. And in the 2D CFT direction, so 2D CFT actually gave deep descriptions about some important scaling limit of 2D statistical physics models. And one of the notable example is the so-called Cadi's formula on the crossing probability for percolation. And this was later proved rigorously by Smirnov. So over the last 2 decades, there is a effort in probability, which is to build a probabilistic foundation of the concept of Liouville quantum gravity, scaling limit random parameter maps, and quantum Liouville theory as a conformal field theory. And the current status of this effort is that now we have achieved a clear global picture with precise theorem, conjectures, and open questions. And my goal today is to present this picture on the sphere and torus as an illustration And the reason I want to also consider torus in contrast of most of the talks in the subject is that a few important points will be clouded if we only focus on the sphere. Okay, so but let me first start to define the quantum Liouville theory on the sphere. There are two approaches to this theory. One is due to Sheffield and Dupont-Miller Sheffield. And this theory is mainly inspired by the conjecture that Liouville quantum gravity is the scaling limit of random parameter maps, and it intensively used the coupling of SLE and Liouville quantum gravity. And the other approach is started by David Kupani, Rose, and Vargas, and this adopt the perspective of constructive field theory. And this is very suitable for studying the conformal field aspect of quantum Liouville theory. And so with Aru and Huang, we have proved that these two approaches on the sphere, they give the same theory. And today in my talk, I will mainly focus on the DKRV approach because it readily extends to torus and heterogeneous surfaces. Okay, so let me first consider a canonical example of a Riemann manifold with sphere topology. So let's C hat to be this complex plane union with infinity, and this G hat is the spherical metric. And then this Riemann manifold is just the unit sphere on the three-dimensional Euclidean space projected to the complex plane. And according to the so-called uniformization theorem for the sphere, given any Riemann manifold with a spherical topology, there exists a diffeomorphism so that the push forward of the metric to the this extended complex plane is conformally equivalent to this spherical metric. And we call this diffeomorphism phi a conformal embedding from this general manifold S to this complex plane. And we know that conformal embedding is unique modulo Mobius transforms on the complex plane. So by the transformation rules of the Liouville theory, we know that to understand the quantum Liouville theory on the sphere, it suffices to focus on this unit sphere. Okay. So quantum Liouville theory is very closely related to the concept of Gaussian free field. So I will first start by giving this definition. Gaussian free field on the sphere is a centered Gaussian process with covariance given by the green function of the Laplacian operator. So I will say more things about these concepts in the next slides. For now, I just want to say that a Gaussian free field is actually a random Schwarz distribution. It's not pointwise defined. Okay. And so let me denote this symbol to be the space of Schwarz distributions on C, which is, and I will let this PG hat to be the probability measure on this Schwarz distributions corresponding to the GFF. And this DC is the Lebesgue measure on the real line. And I also introduce this important parameter Q, which is called the background central charge, which is called the background charge of the Liouville theory. It's related to gamma with the, in this very simple form. Now, this guy, it defines a measure on this product space. Okay, and this is a definition of the Liouville field on the sphere. It is a measure on the Schwarz distribution obtained by a push forward of this measure under this simple additive function. Okay, so this is a definition of a Liouville field on the sphere. Okay, now let me give some more details on the Gaussian free field. So here, so let me define this function to be the metric corresponding to the spherical metric. And then this Laplacian corresponding to this metric is simply given by this. And this delta is the regular Laplacian operator. And then we can define the so-called Dirichlet energy, which is just given by this one. And by the integration by parts, we know that this holds. and this volume is the volume respect to the spherical metric. And then, so suppose these lambdas, they are the eigenvalues of the Laplacian operator. Because of this integration by parts, we know that they are all positive. And so there will be one eigenvalue which is 0, and that corresponding to the constant function, and all the other eigenvalues will be positive. And I'll let this phi n to be the non-constant eigenvalues, eigenfunctions of this Laplacian operator. And then this is a explicit construction of the Gaussian free field on the sphere. It's simply given by this series. Okay. So here is a few comments. First of all, this convergence holds almost surely in the Schwarz distribution space, and actually it holds in some negative indexed Sobolev space, but I will not go into detail. And so I have mentioned that this green function of the Laplacian operator is the covariance matrix of the Gaussian free field. And since this H is only a random Schwarz distribution, what it really means is following. It says that if we consider the covariance of two of this H test against two smooth test functions, then this will be the resulting covariance. And this, so I will not give too much details on the green function, but I will just say that, so locally the green function is given by this log, minus log x minus y. So this Gaussian free field is a log correlated field plus some smooth function. So I have normalized my Laplacian operator to have a 2 pi here. So there's no 2 pi here. And Gaussian free field can be defined similarly in any 2D Riemannian manifold. Okay, so now let me introduce the random geometry governed by the quantum Liouville theory, which is called Liouville quantum gravity. First of all, so let me first introduce the LQG area measure corresponding to a general Gaussian free field. So suppose H is a Gaussian free field, which we defined in the last slides. Then the gamma area measure related to H is given by this. And since H is only a random Schwarz distribution, so far this doesn't make sense. In order to make sense of it, we need to take a regularization and normalization procedure. Namely, so we consider this H epsilon x to be the average over the Euclidean circle radius epsilon around x. And then this normalized limit, it actually converges in probability. And we define this limit to be the random measure. And so we know that this limit, so this limiting procedure have a non-trivial limit if and only if gamma is between 0 and 2. Okay. And this random measure is a so-called Gaussian multiplicative chaos over this Gaussian free field. And this general theory is due to Kahan. So we can also define the so-called LQG metric for Gaussian free field. This is achieved last year by these two group of people, and they were managed to construct a random distance function, dh, out of the Gaussian free field using a similar regularization and normalization procedure. But this construction is mathematically much harder. So the level of difficulty between these two construction can be measured by the gap between these two times. Okay. So I will not give any detail about how this metric is defined, but I will just mention one fact, which is this metric is almost surely determined by the area by some deterministic function. So yeah, this is the only thing we need to know about metric in our talk. Okay, so now I'm ready to define the Liouville quantum gravity random geometry corresponding to the quantum Liouville field we just defined in the last slides. So let X to be the sampled from the Liouville field measure on the sphere. Namely, we sample this pair according to this measure, and then we let X equal to H plus C. So then the random area measure corresponding to the quantum Liouville theory is given by this, which is very similar to this Gaussian multiplicative chaos, but you have this little multiplication here, And now you need to use this volume. And this metric is just given determined by the area in the same way that this metric is determined by this area. Okay, so so now you may wonder that so it seems to be the case that Gaussian free field is a very nice field, and this construction is also very nice. So why bother to introduce all these more complicated things? For example, once we consider this measure, this is actually an infinite measure rather than a probability measure. And we also have these complicated things. So what's the motivation? So for one thing, so for example, here we are consider a spherical metric, but this average is over the Euclidean circle, which is actually not so natural. But here, once we consider this modification, this square root of g hat epsilon is actually the radius, is actually the radius of this circle of radius epsilon under this spherical metric. So this is actually a more intrinsic quantity. And more importantly, this is actually giving the right random geometry that will be corresponding to the 2D quantum gravity considered by physics. So this is my next topic. Recall that Polyakov and other physicists, they predict that the 2D quantum gravity, it corresponding to the Liouville quantum gravity with gamma determined by this. So here, this C gamma is a formula for central charge, which is 1 plus 6q squared, and the q is given by this relation to gamma. And we need this guy to be this magic number 26. And the solution to this equation for gamma between 0 and 2 is given by this number. Okay. And now, now since we have a well, we have the well-defined notional Liouville quantum gravity, we can now make this conjecture very precise. So recall that this 2D pure quantum gravity, it is just the uniform random geometry. And so one way to approach it is to just consider all the discretized random surface and consider this random geometry induced by that. So for this purpose, we consider the so-called uniform triangulation, which is just a uniformly sampled triangulation of a certain size. And this n will go to infinity eventually. So now we just assume every face is an equilateral triangle. Then this guy will become a random Riemannian manifold, which come with an area and metric. Then we can apply the conformal embedding based on this uniformization theorem to embed it to this unit sphere. And this conformal embedding will induce a random area and a random distance function on this unit sphere. Okay. And so here, the triangulation of an example of the so-called planar map. And the triangulation just means that we have a planar map where the face size is equal to 3. Sorry, the face degree is equal to 3. So now we can make a very precise conjecture about this conjecture of Polyakov on the sphere case. So we can set the gamma equal to square root of a third coming from that magic formula related to 26. And then the conjecture would be, after proper rescaling, this discrete random area and random metric coming from the conformal embedding of the uniform triangulation, it converged to the random area and random metric conditioned on the total area to be 1, coming from the quantum Liouville theory on the sphere. So here, since we fixed the uniform triangulation to have size n, so in the limit, we need to fix the random geometry to have a total area. So we just normalize the condition to be 1. And there's an actual technicality, which is, so in the spherical case, we need to fix 3 points in order to fix the conformal embedding. But I will not bother you with the detail of this technicality. And in this kind of conjectures, we expect 2 types of universality. So one is over the types of random parameter maps. For example, we can consider triangulation, quadrangulation, or cubic maps, some other regular maps, or has no constraint on the size of phases and so on. So this is one type of universality. And the other type of universality, which I think would be more interesting, is that it's over the discrete conformal embeddings. So here in this picture, so we have embedded this random parameter map using the so-called information theorem. But actually, there are many other notions of discrete conformal embeddings, which in the limit would approximate the continuum conformal embedding. And notable examples include the so-called circle packing, Tut embedding, and the so-called Cadi embedding. So, so last year, Nina, Holden, and myself, we proved that this conjecture holds in the so-called Cadi embedding. And our proof relies deeply on the understanding of the metric structure, both for the uniform triangulation and the square root of a-third LQG, thanks to these very deep works. But this conjecture is still open for any other conformal embeddings. So in our work, we understand, in a very deep way how this Cadi embedding works, but we don't have any knowledge about all the other embeddings. Okay, this is the pure quantum gravity case. And now let me go to the more general case of so-called 2D quantum gravity coupled with matter. So here, a conformal matter in the continuum, it has two different kind of descriptions. One is a conformal field theory with certain central charge, and another one is the SLE with a certain kappa value related to the central charge that follows. But what is the most relevant to us is discretization, and there are simply some 2D statistical physics models. Notable example includes Ising model, which corresponding to central charge equal to 1/2, and another one called uniform spanning tree corresponding to central charge equal to -2. Okay, so, and then according to Polyakov and other physicists, this 2D quantum gravity coupled with conformal matter, it corresponding to Liouville quantum gravity with a gamma parameter. And the relation between this gamma and the central charge of the conformal matter field, we have to relate it by this magic formula. And so the discretization of the of this quantum gravity coupled with conformal matter will just be the random parameter maps, but weighted by the partition function of the corresponding discrete model. And using this table, we know that this Ising model have a central charge 1/2. So if you plug in this formula, you realize that gamma will correspond to square root of 3. And for uniform spanning tree, we plug in -2 here, and we have gamma equals square root of 2. And the natural conjecture would just be that Liouville quantum gravity is a scaling limit of the weighted random parameter models. Oh, sorry. As in the uniform case, according to the above table. Okay. And so far, this conjecture is not proved for any gamma not equal to square root of a-third. Weaker variance has been proved for many models, and for more details, I will refer to Nina Holden's talk in this conference, and there's also a comprehensive survey by Green, Holden, and myself. And the related important question is to understand the Liouville quantum, the LQG metric for gamma not equal to square root of a-third. In particular, we don't have any counterparts of these other deep works. And one example is that we know that for this uniform case, the scaling exponent of the metric is given by 1/4. But in general, we don't have any prediction about this exponent. Okay. And another important thing is we have assumed that gamma is between 0 and 2. And this is equivalent to the matter central charge is smaller than 1, and the Liouville central charge is bigger than 25. And very recently, people have started to thinking about the case where the matter central charge is bigger than 1. And in this case, what happened is that the Liouville quantum gravity area doesn't make sense anymore because the Gaussian multiplicative chaos theory doesn't apply. But the Liouville metric still makes sense. And I will not go into any detail of this, and I will just refer you to Yuan Green's short video on YouTube and Nina Holdings talk. Okay, so now I will move to the case of quantum Liouville theory on torus. Similar to the sphere case, I will first choose some very canonical torus manifold. So given a tau on the upper half plane, we can consider a flat torus, which is given by the identifying direct opposite sides of this parallelogram. Okay, and then the uniformization theorem for torus says that if we have a Riemannian manifold with torus topology, then there will be a tau on the upper half plane, so that this manifold is conformally equivalent to this torus, this flat torus. And similar to the sphere case, by the transformation rule of the quantum Liouville theory, in order to understand the case on the torus, we only have to focus on these flat torus. But there is a very important difference between the sphere and torus, is that on torus, so these two different flat torus, they are conformally equivalent if and only if tau and tau prime is related by this relation. So, and this means that there is more than one conformally non-equivalent torus. So I will use M1 to be the space of all the torus metric modulo conformal equivalence. And then because of this fact, this modular space is equal to the quotient of the upper half plane by this so-called modular group. And the generator of the modular group is generated by this shift and this inverse. So this is a discrete group. Okay. And now let me define the quantum Liouville theory. So in the torus case, the since we have flat metric, the Laplacian operator on the torus will just be the regular Laplacian operator, and we can define similarly the Gaussian free field, and then we can consider this p tau as the probability measure on the Schwarz distribution on this torus, and we can consider this Lebesgue measure. And then similar to the sphere case, the Liouville field on the torus is just simply by the push forward of this measure on the product space of this under this additive function. Okay. And we can similarly define the quantum Liouville, the random geometry, which is the gamma LQG corresponding to a quantum Liouville field on torus. So now we just sample a Liouville field using this measure, and then we define the area this way, and then we define the metric. So there's nothing new about this compared to the sphere case. So, and in the general case, the Liouville field is defined this way. So here, we will still consider this product measure, but we have to weight it by this term. And this kg is the so-called scalar curvature of the metric, and this pg is the probability measure of the Gaussian free field. And since both the unit sphere and the flat torus, they have constant curvature, you can actually check by hand that this term is equal to 2qc on the sphere case and 0 on the torus case. And that's why on the sphere case, we need to have e to 2qc for the Liouville field. And on the torus case, we don't have this term. We will just have this product measure. Okay. And so in physics, this quantum Liouville theory is defined as a quantum field theory. And it's formally defined by this measure, where this guy is the so-called Liouville action. And David, Kupani, Rose, and Vargas, they were able to realize this formal measure as a mathematical term. So here, this Dirichlet term, they will just corresponding to this product measure. And this volume term, it actually corresponding to the random, the total measure of the LQG measure. And then this Liouville action will just be given by this measure. So this is first done on the sphere by DKRV, and then it is later extended to other surfaces. Okay, And now we can make some similar conjectures about the scaling limit on the torus to the Liouville quantum gravity. So here, similar as the sphere case, we consider uniform triangulation with torus topology with size n, and we also assume every face is equal to triangle. And but now this torus triangulation, it will conformally embedded to a flat torus with some random tau n in this model space, and this will also induce a area and the distance function on the random flat torus. And then the scaling limit conjecture will be similar. We set this gamma equal to square root of a third, which corresponding to the central charge equal to 26. And then this tau n will converge to some random variable in this moduli space. And this metric will converge to this Liouville quantum gravity condition of total volume to be equal to 1. So this conjecture, in my opinion, is not much more difficult than the sphere case. It just one is on so basically once you know what happened on the sphere, then you can try to localize the geometry and then transfer to the torus. Yeah, but what is perhaps very surprising is that there's also a conjecture about the law of this random moduli in this case. So it is actually conjectured in physics that this law of the random moduli have a very simple and explicit density. It's just given by this formula. And this is a fact which is so far very mysterious in probability. I can only say that it is related to this magic number 26. So far, I couldn't see more. So more generally, we can consider conformal matter quantum gravity coupled with conformal matter fields. So suppose we have a conformal matter field with central charge Cm, and then similar to the Liouville, similar to the quantum Liouville theory, this just means that given any Riemannian manifold, we can assign a measure on these functions on the Riemannian manifold. And so since it is a conformal field theory, this identity holds, which means if we have two conformally equivalent manifold, the random measure, the measure on random functions will only differ by a multiplicative constant. And we define the partition function of this theory of this conformal matter to be the total mass of the this measure. Then if this manifold has torus topology, then by this identity, this function is actually only defined, depends on the conformal class of this manifold, which means it is a function on this moduli space. So in general, this measure corresponding to this conformal matter field, it might not have a mathematical definition, but this this partition function usually does. And in this case, we still have a similar conjecture for the scaling limit of random parametric maps coupled with this conformal matter field. And in this case, the conjectural random moduli is given by this formula. So basically, we take the random moduli coming from the pure quantum gravity case, and then we weight it by this normalized partition function. And it is also a very mysterious open question to see it from the scaling limit of weighted random parametric maps. So to conclude the discussion on this random geometry side, so I will mention that this quantum gravity on general genus G surfaces, it also induces random measures on this moduli space of genus G surfaces in a similar fashion. And so these quantum gravity intuitions, they give deep relation between integration of moduli space and enumerative geometry and integrable systems, but I will not get into details. So now I will go to the conformal field theory perspective of the quantum Liouville theory. So I think I might only just have 7 or 8 minutes, so I will be brief. So in the conformal field theory aspect, the most important concept is a so-called correlation function. And for quantum Liouville theory on the sphere, the correlation function is defined as follows. It formally defined by this formula. So here, so we know that this Liouville field is just it's like a Gaussian free field plus some constant. So this is a Schwarz distribution. But this guy can be made sensible by applying the Gaussian theorem to this Gaussian measure. So there will be a shift. And then, so we include this so-called cosmological constant because only if we have this term, we can ensure that this correlation function is finite for some non-trivial range of alphas. And we can define correlation function on torus in a similar way. And the key property of quantum Liouville theory as a conformal field theory is the following. So suppose we have this correlation function where the points are related by some Mobius transform on the sphere, or if these torus parameters, they are related by this modular group, then the correlation functions, they will be related by some simple factors. So this is the bound of parameters for the finiteness of correlation function. So here there are two conditions. One condition is every alpha has to be smaller than Q, and the other one is the total sum has to be bigger than this Euler characteristic times Q. And for the sphere case, the Euler characteristic is equal to 2. And if you apply to these two identities, we realize that we have to at least have 3 values of alpha in order to have a non-trivial range. Okay, and so because of this conformal invariance, we know that if we only have 3 points, since every 3 point on the sphere can be related by a Mobius transform, so this correlation function, this 3-point correlation function, can actually be factorized into this simple powers times a function which does not depend on these 3 points. It only depends on alpha 1, alpha 2, and alpha 3. And this constant is a so-called structural constant of the quantum Liouville theory. And in the remarkable paper by Companion, Rose, and Vargas, they show that this constant is actually given by explicit meromorphic function. So I will not give the detail of this meromorphic function, but I will just but I can show you that this is a very complicated function, but you can write down the formulas. And mathematically, it is a very deep fact about Gaussian multiplicative chaos, because if we look at the definition of this correlation function, it's at the end of the day, it's all about the distribution of this Gaussian multiplicative chaos measure. Okay, and this formula is called DOZZ formula because it is originally predicted by physicist named DOZZ. Okay, so as I mentioned at the beginning of my talk, so Liouville, Polakov, and Zamolodchikov, in order to solve the Liouville theory, they realized that 2D local conformal symmetries, they impose very strong algebraic constraint on all 2D CFTs. In particular, they discovered that you have the formally you have the so-called operator product expansion. So here it means that if we have the product of 2 terms like this on the left-hand side and on the right-hand side, I can write it as a sum of just 1 term, but with a variable p, with a variable p. And here, so all this other stuff like this dot 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 and this exponent, they are universal for all 2D CFTs. The only thing which will depend on a particular CFT will be this set where you do the summation and this constant. And there's a program called conformal bootstrap, which is an algorithm to compute all the correlation functions of a 2D CFT in terms of the spec and this constant following this OPE procedure. And for the quantum Liouville case, the input is given by the follows. The spec is given by this line, and this constant is just the DOZZ formula. So quantum Liouville theory is a primary example of CFT with a continuum spectrum. Okay, so I want to say that the reasoning of the conformal bootstrap for quantum Liouville theory is very hard to make sense probabilistically because this e to the px is doesn't make sense because p is a complex number, so we couldn't apply the Gaussian theorem. But they do output some very precise conjectures on the correlation functions of Liouville theory, which are just some very deep fact about Gaussian manipulative chaos. So, and here is the example of conformal bootstrap applied to a 4-point correlation function on the sphere. So here, following OPE, so this is the prediction. And here, so the most important term is this DOZ formula, which is already computed by mathematicians, and now we have a very important power series called conformal block, and this is also universal for all CFT. So if you have another CFT and if you want to compute the 4-point correlation function, the only thing we need to change is this set to some other set, and then this number will be changed to other C alpha 1, alpha 2, and P. And the conjecture is that whenever this correlation function is finite, this formula should hold. And this is a very deep statement about Gaussian manipulative chaos. So in a very recent remarkable paper by Guillermo Compagni, Rose, and Vargas, they show that if gamma is between 0 and square root of 2, then this formal power series defined called conformal block, it actually converge, and the conformal bootstrap actually holds. So their method is to rigorously make sense of this OPE for the case gamma is between 0 and square root of 2. And their idea X tends to general case of n-point torus or n-point sphere. And so here is an important open question, which is extend the conformal bootstrap to the case where gamma is between square root of 2 and 2. So this GKV approach, it has essential obstructions to extend to this range. But on the other hand, most of the interesting gamma values from the quantum gravity perspective is actually falls into this range. So we have mentioned 3 values in my talk. One is pure gravity, and the other is Ising model, and this is infinite spanning tree. They all falls into this range. And the more open question is, can you see these complicated formulas from the scaling limit of random parameter map perspective? So here, so this is another example of conformal bootstrap applied to torus. And here, so we also have this formal power series, which is called 1-point torus conformal block. So in a torus case, if we apply the condition on the boundness of the correlation function, we realize that we only need 1 alpha to make it finite, and alpha is between this range. And right, and in working progress by GKRV, they can extend their method to prove this formula also in the case gamma is between 0 and square root 2. Okay. And the conformal block on the sphere and on the torus, they are both formal power series defined by the so-called Virasoro algebra, which is the symmetry algebra of 2D CFT, whose series coefficient can be computed recursively. So for some special parameters, these power series have some integral representation, which is good enough for many conformal matter field. But for Liouville field, since we have this integration over this whole line and all these parameters in this general range, so we have to allow all the parameters to be generic. And in this case, these power series are very difficult. So one of the important facts about conformal block is that there are some general relation between quantum Liouville theory and certain 4D gauge theory. And using that correspondence AGT conjecture that conformal block actually is equal to the Nekrasov partition function, which was computed by Nekrasov. And I will not go into the detail of this formula, but I will just give you an example of the formula on the torus case. And it basically expresses the power series coefficient of this torus conformal block into some random Young diagrams. Okay. So the last term I will present in my talk is a very recent work of Gausso, Remy, Ethan, and myself. So what we did is we provide a Gaussian multiplicative chaos representation of this very complicated function, 1-point torus conformal block. So the statement is the following. So we consider this expectation. So here, this H is the Gaussian free field on this flat torus restricted to a unit interval. And this measure is the Gaussian multiplicative chaos random measure. And this Q is the given by this e to the I pi tau. And then, and these theta and z, they are some explicit meromorphic functions that I will not give the detail. So, so we first define this probabilistic quantity. It's a simple expectation over some GMC measure, some moment of GMC. And then we show that this guy, this function as a function of Q, it admits a analytic continuation around this interval, including the origin. And then we show that as a power series, this power series is actually given by this conformal block. In other words, it's given by this formula. So this is another, to me, it's a quite deep statement about Gaussian multiplicative calculus. And as a corollary, we show that this power series converge when Q is smaller than 1 over square root of 2 for all gamma is between 0 and 2. So here, this number is currently just due to some technical constraint to our method. So the real answer should be Q between Q just smaller than 1. And for GKRV approach, I think they can prove this bound for Q between smaller than 1, but they have to assume gamma is between 0 and square root of 2. And they have to assume that, and they can only prove this for almost every P, not every P. Okay. And in the current working progress, we are trying to show that this modular group, it acts on the linear span of the space of the probabilistic conformal block that we defined in the last slides. And this means that if we use an element of the modular group to transform one of these conformal blocks, it will be given by some linear combination of other conformal blocks. And then because that this range, it actually covers the fundamental domain of this modular group on the alpha half plane. So this will show that this conformal block is converged for every cube smaller than 1. And so I want to mention that this GKRV approach is very, it even couldn't extend to gamma equal to square root of 2 by continuity. But since our approach to the conformal block is just given by a simple GMC, our approach can extend to the case gamma equals square root of 2. So if we combine these two approach, we will show that the conformal bootstrap actually holds for gamma equal to square root of 2. And our future goal is to extend this work into more general case to include the 4-point sphere. Okay, so I think my time is up. And so I will just conclude with a few questions that I mentioned in my talk. And thank you very much for your attention.
Thank you, Xin, for the nice talk. Now we have time for discussions. Any comments or questions? Everybody? I have a question on the background of the study, Xin.
Okay.
There is another class, a class of models for phase transition called spin classes, which can be thought as the
like a random
model
IC
in
model.
random environments.
Right.
And a variation of those models is the generalized random energy model. Suggested by Tahita and Yuela and so on in the 80s. Could the stuff you explained here contribute in some way to the study of those models? Because I know in the study, most of the studies.
Yeah, so I think the extreme values of those like random energy models, I think they are actually related to Gaussian multiplicative calculus. Yeah, right. And I think they are like, for example, if you consider the fluctuation of the extreme values of these models, I think there are some conjectures on the distribution of what is the fluctuation of the maximum around the mean. And I think those random variables are actually given by these Gaussian multiplicative calculus.
Good. Any other questions? Yes. There's some voice. Okay, maybe in some cases the Gaussian fields can be constructed by continuum random trees. Is that the case?
I mean, so this so Gaussian free field in 2-dimension is so the correlation function is given given by minus log x minus y, so it has some tree structure. But so if you use random trees, I think you will get some log correlated field, but it may not be the just the exact Gaussian free field. So in the Gaussian free field, the correlation function is given by minus log x minus y plus some particular smooth function, and and that smooth function guarantee the conformal symmetry. And I think so if you use trees, you will get something which is very similar to Gaussian free field in some qualitative properties, but for some properties involving conformal symmetry, I think that might not apply.
Okay. Any other questions? If not the case, I think it's almost the time. Anybody, if you want to discuss this or other topics, you may go to the coffee garden, and then we may end this session. Finally, let's thank Xin for his nice talk.
Thank you so much.
Thank you.
Okay.
So, okay, goodbye, everybody.
Thank you.
Bye.
Thank you, Siva.
Thank you. Welcome. Yeah.
Bye-bye.
Yeah, we're all set. Thank you very much.
哎，最近你已经那个 move 了是吧？
对对对，我其实是3月份就搬过来了，因为那个纽约那边疫情比较严重嘛，然后我提前搬过来。
因为我看那个介绍说是你是秋季才会过来。
是，但是因为就是那个疫情之后，那个哥大那边就没有，就是那个上课呀什么都不在校园了嘛。就我实际上即使在纽约，我也去不了校园。
纽约这边你3月份过来，那个课程呢？现在疫情这个。
我今年秋天不用教课。
Okay, Zhenghu, I have to close the room, so you can continue the coffee garden maybe this discussion.
Oh, sorry, thank you.
对
，OK，
这还有一个 coffee garden 是
吗？谢谢啊，再见。
Yeah. Just a note to everybody, I will close the room and you can continue discussions in the coffee garden or the live discussions. Thank you.
Okay. Thank you.
Bye. Thank you.